gonna punch you in the face.
Get close and then you got something else.
You're a liar.
So, it says, logarithms provide a way to work with the inverses of exponential functions. So we're going to start out today looking at exponential functions, and then logarithms are the inverse of that. So we're going to switch the x and the y and solve it. Exponential functions model what some might call explosive growth. So one of the things that you're going to see today is that exponential functions increase really rapidly. Okay, logarithmic functions, because they're the inverse, grow very slowly. Decibels, you guys know what decibels are, right? Seahawks game and all that kind of stuff, and setting the decibel record or whatever, are logarithmic. Okay, so that's an example of a logarithmic function. And when sound energy increases dramatically, the decibel values only go up a little bit. But if you go the other way around, if you go up a few decibels, the inverse, that means the sound energy increased a lot, and so that can really cause some problems. All right? Oh yeah, math is fun, everybody loves it, yay, yay, yay. All right, section 7.1 is on exploring exponential models, and our objective is to model exponential growth and decay. So we are going to start with a little problem today, a little puzzle. What? 434, thanks. We're going to start with a little puzzle called the Tower of Hanoi, and I used to actually have a physical one of these, where you have 5 rings on a peg here, and your goal is to move these rings onto one of the other 2 pegs. And the rules are that you can take one from the top and move it somewhere else. Okay? You can only move 1 ring at a time, so you can't grab 2 or 3 or the whole stack, because then that would be dumb and easy. And you can't place a big ring on top of a small ring. Okay? So this has 5 rings right here, and so what we're going to do is we're going to try to figure out what is the fewest number of moves needed to move all of those from one ring to another ring, from one peg to another peg, okay? And we are going to we're going to do this by starting out easy. So if I have 1, and I want to move that, actually they want us to move it from the leftmost peg to the rightmost peg. I want to do it in the fewest number of moves possible. So if I have 1, the simplest case, I can take that and put it right there, yay, in one move.
Hope you enjoyed it.
Congratulations, hope you enjoyed. Okay, so we are going to keep track of that as we go. 1 ring required 1 move. Okay, now I am going to make this into 2. Anybody like to come up here and try to do this? Okay, Lizzie, come on down. Okay. So she takes the top one and she puts it.
Isn't it like the x minus 1?
Middle.
Where you're looking like that one.
Nice. Okay, so when we had 2 rings, it took her 3 moves to do it. Okay, and she even got it over here to the right. We could get them all into the middle, and that would be okay too. Would anyone like to try it free? Okay, come on. Can't put a bigger one on top of a.
That would make it so easy. You just put them all in one.
I don't think I can do it, guys.
Okay, remember we're trying to do it in the fewest number of moves possible.
I
Can't put a big one on top of a small one.
Put the yellow on the right side.
Yellow
all the way to the right.
Put the yellow one all the way on the right.
Then put the green small one on
Put the
top.
small one on top of that.
Oh yeah, do it. It's just weird. So just
I'll put the green. Oh, there you go.
You gotta move the little one all the way to the left.
Yeah, it
No,
was.
you're good. We'll put that in the middle. Put that one on top.
I thought we had to get it all the way.
Yeah, you're supposed to get all the way over there, but we're gonna count that as good. So that took 7 moves, okay? And she could have done the way this puzzle wants is they want us to go all the way to the other side. So if she'd have just reversed the order that she did it in, it would have worked out to get it to there in only 7 moves. You had the right idea, okay? All right, so how many moves do you think it's going to take for 4?
11.
10?
11.
11? 18? 13?
17.
Up by
It's gonna
2,
be
up
an
by
odd
4, up by
number.
6?
It's gonna be an odd number.
Okay, hopefully you guys are looking for patterns a little bit. Lizzie? 15? 13, 15?
Yeah.
All right, would anybody like to give that a try? With 4, Sydney?
Oh, are you sure? I think it's 30.
You think it's 13 because it went up by 2 and then up by 4, and so now it's going to go up by 6?
I think it's gonna be 36. Yeah, I know.
Oh, it's count as a move.
Oh, okay.
Right. Yeah.
Why did that count as a move?
I think because she took it off and she put it back.
Oh.
Well, you're okay. It's just that being, you should be able to do that.
Yeah, okay.
Yeah, put that one always to the left. Always to the left. The yellow one on the left. Now put the little one on top of that one.
No, see, you got this to the right.
Close enough.
Okay, so she got it. How many moves did it take?
It's 19.
19. But some people think there's maybe an easier way to do it. Hit the reset button.
Do it again.
You gonna try it? You gonna show us the easier way?
Rubik's Cube in like 30 seconds, you can do this.
No? No? Try and do something fun. Thank you. Try and have a little game.
Just making everybody
I think I got it.
It's like nap time here, it's so warm, it feels good.
Yeah.
What do you say, Nate? Degree? Oh,
no, you're not.
Whoa, go back. Where do I want to go now? Over here? Oh my gosh. Oh, what did you say? Okay, so that's the lowest number that you can do with that one, and that one would be
Hey, I was right, it was an odd number.
15. Okay, so those of you that said 15, what's the pattern that you're seeing?
Odd number.
Go ahead. Hey, put your phone away. No, that's not away. That's just sitting on your desk. Put it away in your pocket.
Oh, I
Oh, you
see.
just put it on your desk. It's right there. That's not away.
over.
Who has theirs on their desk? Brooke?
Right there.
She's not making announcements about NFL trades.
I see.
Five's gonna
Okay,
be
Lizzie?
Five's gonna be 30.
Okay, so it went up 2, and then went up 4, and then it went up 8. And so you're thinking the next time it's going to go up 16. Okay, so that would be 31. Should we try it?
I think. Wouldn't you just multiply the previous number and add 1?
We're going to talk about that in just a second. Okay, so now technically I want this to be over here, right?
Yeah.
All right, let me see if I can do it in 31. Someone just call me a... Oh, missed it. They didn't count that, did they?
No.
31.
Not bad. You go up to 6.
That's so smart.
Let's try the next
Thank you,
one.
thank you. All right, so the main thing is 31 is correct. Okay, so we have found the pattern. However, if you recall, the most wonderful reindeer of all, it says that they want 10 rings and 20 rings, okay? And so we're not going to just keep adding and adding and adding and adding and adding. We would like a formula, y equals, so this is my x and this is my y. What can I do to these numbers right here? What can I do to go side to side? Colton? So 1 times, nope, there's a 2 in there somewhere, right?
Yeah.
Okay?
It's gonna be 2x.
It's going to be 2 times x.
No, it's gonna be x squared.
You think it's going to be x squared? Ooh, now we're talking, we're getting some exponents in here. We are, after all, studying exponential functions. Okay, so this squared, 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 6.
Minus 1.
But it doesn't work for y, you go minus 1.
What?
Well, you go minus 1, but
2x plus 1. But 2 times 1 is 2, plus 1 is, yeah. Okay, here's the thing that you need to think about. You're very close with the 2's in there, and the 2x, and the x squared. However, the way that these functions are different than ones that we have studied before is 2 is the base, okay? So if I go 2 to the first power, what do I do with that to get 1? Subtract 1. If I go 2 squared is 4 minus 1 is 3. 2 cubed is 8 minus 1 is 7. 2 to the fourth is 16 minus 1 is 15. And 2 to the fifth is 32 minus 1 is 31. Okay? So what's different about these functions that other than the ones that we've studied before is that the variable is the exponent. And that's why, I'll turn it down, that's why they are called exponential functions, because the variable is the exponent. Yes? 2 to the first power is 2 minus 1 is 1. Okay? So if we are now going to answer the book's question and see how many moves would it take with a stack of 10. What'd you say? 1023. Good, because I would have to go 2 to the 10th minus 1. And if I did that, I would get 1023. So it would take 1023 moves to do that. You guys want to see me do it?
Yeah.
No. How about 20?
1,048,575.
1,048,575.
575.
Okay? No, that would take forever. Okay? All right, but the key is that this is an exponential function because the variable is in the exponent. Okay? And so that's the types of functions that we're going to study in this chapter. So to start with, here is, as promised, your general form of an exponential function. It's y equals a number times another number to the x power. There are some restrictions on what b can equal, and b is called the base because it's being raised to a power. B has to be greater than 0, and b cannot equal 1. Why can't b equal 1? Because the answer would always be 1, because 1 to any power is always just 1. So that would not be a very interesting or useful function to do anything with. Why does b have to be positive? Because if it was negative, there wouldn't be 2 answers, but let's say it was negative 2 instead of 2. What's negative 2 to the first power? Negative 2. What's negative 2 to the second power? 4. So we got a negative number and then a positive number. And the negative 2 to the third power would be negative 8. So it's negative again. And and then positive 16, and so it bounced back and forth between being positive and negative, which is confusing, and so we just don't want to deal with it, okay? All right, so today we are going to start out very slow, very simple. I'm sure you guys that have spies in second period, they already told you that we had an easy assignment. So let's take a look at some graphs here. Let's look at the graph of y equals 2 to the x. Give me a point on that graph that you would know.
0, 0.
0, 0? How do you get 0, 0 out of that? 2 to the 0 power is what? 1. Any number to the 0 power is 1, not 0. So one of the points is going to be 0, 1. Okay? Give me another point. What? What? 2, 4. Because if I plug in 2 for x, 2 squared is 4. 1, 2, 3, 4. Okay, so that's another one. Not sure why you skipped 1. Right, if you plug in 1, then you get 2 as an answer. What do you get if you plug in 3? You're your own worst enemy. 8. 4, 5, 6, 7, 8. And so if I sort of smoothly connect the dots here, the next one would be 16, which would be way up there. It's not a parabola, okay, because it's increasing way too quickly. All right. The other reason why it's not a parabola is what do you get if you put in -1 here? What is 2 to the -1 power? What? Right. 2 to the -1 is 1 over 2 to the +1, which is just 1/2. And so, where's your parabola now, Riley?
Well, you don't have
That's what I thought.
So what
All right.
happens if we were like, if we were just?
What's 2 to the -2? Right, because 2 to the -2 is 1 over 2 to the +2, which is 1/4. What's the next one going to be? 1/8, and then 1/16, and blah, 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 blah. So what's going to happen is it's going to get... Right.
It can never be 0.
Yeah, right. It's going to get closer and closer to the x-axis, but it's never going to touch it because it can never be 0, okay? Because even if you raise it to a really big power, 1 over a positive number will always be greater than 0, okay? So that is what a general graph of an exponential function looks like. All right? You happy with that? Yeah. All right, let's look at a couple more and see what happens when we change that base number. So give me a point on the graph of y equals 4 to the x. 0, 1, because if I plug in 0, 4 to the 0 power is 1. Okay, good. If I plug in 1, 4 to the first power is 4. What do I get if I plug in 2? Yeah, I get 16 already. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this one you should be able to see is going up in a hurry. Because the next point would be 364. Okay? So when you do these graphs today, you're going to want to think about the scale you use on your y-axis. I probably should not have gone by ones. What happens as I go to the left? What's 4 to the -1 power? 1/4, so I'm already way down here. What's 4 to the -2 power? 1/16, so I'm already practically touching the x-axis, so it goes way down like that, okay? So that takes off way faster because the base is 4, and it also is way flatter over here. How about if the base is 1/3?
It goes the other way.
It goes the other way? What do you mean by that, young man?
It goes.
Oh, I see what you're saying. Can you show me why? Explain to me why? You just because? Oh, because you did it on the calculator, okay. Give me some points on y equals 1/3 to the x. Okay, once again 0 and 1, because 1/3 to the 0 power is also 1. What's another point? 1 and 1/3, good. And so that is why Riley said it's going to go the other way, because now when I raise 1/3 to positive powers, it gets smaller and smaller. What's 1/3 squared? 1/9. So now that's way down here. And then 1/27. So now on this side, it's getting closer and closer to the x-axis. And then what happens over here when I put in negative exponents? This is a little bit tricky, but if I do 1/3 to the negative 1, that's like 3 to the positive 1. Okay? So if x is negative 1, then y is 3. What's 1/3 to the negative 2? 9. So 3, 4, 5, 6, 7, 8, 9. So like Riley said, it's going to be the opposite, flipped around, okay? All right, and then finally, let's look and see what happens when I put a number in front of the function. What's the y-intercept now? What is, when x is 0, what do you get? 2, because 3 to the 0 power is 1 again, and 2 times 1 is 2. So this time this is going to cross the y-axis at 2. So this is the y-intercept. There's a hidden 1 in there, that's the y-intercept of that one. There's a hidden 1 in there, that's the y-intercept of that one. So the number in front of the function basically is the y-intercept. What do you get if you plug in 1? 6, because 3 to the first is 1 times 2 is 6. 1, 2, 3, 4, 5, 6. What do you get if you plug in 2? 18, good, because 3 squared is 9. 2 times 9 is 18. So that's going to be up here. So that's going to increase at an even faster rate than the other one. How about if we go this way? What do you get if you put in negative 1? 2/3, very nice. 2 times 3 to the negative 1 is like 2 times 1/3, which is 2/3. So that's going to be right here. How about 2 times 3 to the negative 2? 2/9, yeah, because that's 2 times 1/9, and that's going to be 2/9, so that's going to be way down here. So that's going to look something like that, okay? So the shapes are similar. This one's flipped, and then that one goes up at a different rate, all right? Fun stuff. All right, so there's two types of exponential functions. One is exponential growth, and one is exponential decay. So exponential growth is when it's increasing really, really rapidly. Exponential decay is when it is decreasing really, really rapidly. Which color graph is an example of exponential growth?
The green and the red.
The green and the red are both exponential growth because as you go from left to right, they're getting bigger and bigger and bigger. And then that means the yellow is exponential decay because it is going down as we go from left to right. All right. This line right here, the x-axis is called an asymptote. An asymptote is a line that a graph approaches as x or y increases, but it never actually gets to that spot. Okay. How could you tell from looking at these two functions that they will be exponential growth, and this one will be exponential decay?
Because they're whole numbers and
They're bigger than, right, they're bigger than 1. So we're multiplying by a bigger number every time, so it's getting bigger and bigger every time. So this is growth and this is growth. How do you know that this is decay? Because it's less than 1 but greater than 0. Okay? So in between 0 and 1 is decay, bigger than 1 is growth. All right? So 12 times 0.95 to the x, growth or decay? Decay, because the 0.95 is less than 1. And what is the y-intercept? The y-intercept is 12, right, good, because it's the number that is in front. Okay, nice. How about this one right here, growth or decay? Growth, because 2 is bigger than 1, so that's going to be growth. Stay away from me. Don't touch me, you're growth. And then the y-intercept is what? 0.25. All right. Okay, how about if we completely change gears and ask the same question about a banking problem, which these are closely related to. if you put $1,000 into savings and you get 5% interest, you better hope that that's a growth function. You want your money to increase. That's why you're giving it to the stupid bank in the first place. What is the y-intercept? 1,000. Yeah, because you're starting with $1,000. So the y-intercept is
Is it times 4 to the?
what? We'll talk about those mañana. Okay? All right, so y equals 3 times 4 to the x. Growth or decay? Everybody now. Growth. Y-intercept is 3. Y equals 11 to the 0.75x. Growth or decay? Decay. And the y-intercept is 11. Putting money into a savings account is an example of growth. And in this case, the y-intercept would be 2,000. All right, so we are going to talk a little bit more about the growth and decay factors tomorrow. I'm going to cut it short right there and let you work on some of these graphs on your own. And I'll leave 439.
What? Well, I think it's in my backpack actually.
Yep. If you want small square graph paper, that's by Donovan in the cupboard there. You want some of that. And you can do all of this on graph paper if you want. Nope, by Donovan. Not, I didn't say by Nate. Come on now. Riley, bring a chunk of it out here for us.